Welcome to the UGC lecture series. This is the E-PG Pathashala lecture series on computer science, and we are talking about the paper data structures, and this particular module is about binary search trees. We have two modules on binary search trees. This module will talk about the introductory concepts of binary search trees. This is the team responsible for the development of this module. Now, let us look at the learning objectives of this module. This module we are going to first understand the concept of binary search trees, what does it mean and the concept of that. Then we are going to discuss the searching operation of binary search trees. This is a very important operation as far as binary search trees. We will see how as we go along, and then to describe the in-order traversals of binary search trees, and to explain the successor and predecessor relations associated with binary search trees. We will go why we need to talk about this, we will discuss later, because these two are some operations that we need for other operations of binary search trees like insertion and deletion, which we will be talking about in the next module. So, the key words here are binary search trees, successor and predecessor. So, let us first look at what are binary search trees. So, a binary search trees, it is sometimes also called as lexicographic trees, is a type of binary tree with a special organization of data. So, it is still a binary tree. Remember, the binary tree, it can have 0, 1 or 2 leaves, that remains the same, but the organization of data inside the binary tree is different. That is why it is called binary search trees. As you can see from the name, the binary search trees have been designed in order to make search easier, and especially it is based on the concept of binary search. So, this why should we do this organization of data? That is the next question you would ask. This data organization leads to order of log n complexity for searches, insertion and deletion in certain types of the BST, balanced, but also in general. We will go later on into balanced binary search trees. We are not discussing that now, but even in the case of insertion deletion, it takes of the order of log n time, which is a very important concept, important need when we talk about search of data, okay, in dictionary and so on. So, what are the properties when you associate with any binary search tree? It is what are the maximum number of leaves, maximum number of nodes, and the average depth of those nodes. That is also important. So, these are some of the properties that you associate with any tree, and so also for binary search trees, that is the number of leaves, the number of nodes, and the average depth of the nodes. Now, let us look at what is the meaning of binary search trees. So, first, a binary search tree is itself a binary tree that we have already discussed, but it has some special property which is called the BST or binary search tree property, which is given like this. So, for all nodes x and y, if y belongs to the left subtree of x, then the key at y is less than the key at x, and if y belongs to the right subtree of x, the key of y is greater than the key of x. This is true for every single node of the binary search tree. So, we can assume that you can have duplicate also, but here we will assume that the keys of the binary search tree are pairwise distinct. Before we go further, I wanted to tell you that we are talking about again keys. So, key is the node value, and based on that value only we are talking about all these nodes and their organization. So, just to repeat, all items to the left subtree are less than that of k if you look at the figure. Similarly, all items to the right subtree is less than or equal to the root. Now, this is not true for only the root node, it is true for every root of a subtree. So, each subtree is itself a binary search tree, or it follows the binary search tree property. So, this is the organization of the binary search tree. What do you mean by less than? That is a question you will ask. Less than, if it is numerical, you know the value what is less than. If it is alphabetical also, less than alphabetical order. That is why it is called binary search tree, or sometimes it is also called as lexicographic tree, especially when you are storing the nodes have keys that are alphabetic strings. So, lexicographically it is ordered, that is why it is called a lexicographic tree. Now, let us look at the binary search tree property. Stored keys must satisfy the binary search tree properties, stored keys. Okay. So, if you take this all trees to the left of the root 56 here is less than 56, we have seen the property there, and all keys to the right in the right subtree of this particular tree is greater than 56. So, that is all keys is greater than or equal to 56. We do not consider equal to, because we are assuming that there are no duplicate keys. If there are duplicate keys, it is always put on the right hand right side of the tree root. Okay. So, in a BST the value stored at the node of a subtree is always greater than any value in the left subtree and is always less than any value in the root tree in the right subtree. So, this right subtree, left subtree and the root if you take of any node in any subtree in the binary search tree, to the left all the values of the keys will be less than the root, and to the right subtree or in the right subtree it always will be greater than the root. So, this is the binary search tree property. Okay. Now, before we go further, that means we should organize it in such a way, but before we go to that, let us look at what do you mean by the smallest element and the largest element. What do you mean by smallest element? Smallest numerical value or smallest alphabetical value in the binary search tree. So, the smallest value or element will be the leftmost element in the binary search tree, and the largest element will always be the rightmost element. Now, how do you define this leftmost, rightmost? This is based on the binary tree that we saw earlier when we did traversals and all that. We will come to that later. And the average depth of a node is of the order of log n, and the maximum depth is of a node is of the order of n. Now, this is the reason why our time for searching and all those take less, I mean is fixed. So, that is the property. So, if you look at this tree, you will see that this is the smallest element as I define. This is the leftmost element. What do you mean by leftmost element? Is the leftmost element of this tree, and it will be the first element that comes in a in order traversal. We will come to that later. And this is the largest element, that is the rightmost element is the largest element in this particular binary search tree. So, okay. So, now let us go further. Let us look at some examples. So, binary search tree, this is an example of a binary search tree where we have taken alphabetic nodes. Now, this is again a binary search tree. Please note, a binary search tree does not have to have it need not be a complete tree. So, it can have 0, 1 or 2 nodes, that is fine. Now, look at an example which is not a binary search tree. There are different reasons why it is not so. If you look at this part of it, it is not a binary search tree because it is not binary, okay, that is obvious. Then the left subtree, the key is greater than the root, then also it is not a both cases the left subtree is greater than the root, then it is not a does not follow the binary search property. So, this is not an example of a binary search tree. Now, let us go to the next topic, which is the duplicate entries in a binary search tree. So, I told you can have duplicate entries, but most cases when we talk in general we do not say, but the binary search tree as such does not disallow duplicate entries. If there is a duplicate entry, it is always put on the right subtree. Okay. So, if a duplicate is there, it is always put in the right subtree. Now, let us look at binary search tree. You can view it as a data structure that can support dynamic set operations. So, we are looking at search, minimum, maximum, predecessor, successor, insert and delete. These are the operations. If you look here, search is normal for any data structure, minimum value, maximum value has significance because we are talking about a binary search tree where the organization of data is important. Then we talk about predecessor and successor, but predecessor and successor in a binary search tree is relevant, and when we talk about predecessor and successor, we are talking about a predecessor in an in-order traversal and a successor in an in-order traversal. That is what we are talking about generally, and then insertion and deletion is true for any data structure. So, can be used, where it can be used? It can be used for representing or storing dictionaries or priority queues, and a basic operation that take time proportional to the height of the tree. Now, we are coming to a new concept. It takes approximately equal to 0 to, order of h, where h is the height of the tree. Okay. Now, we talk about ordered dictionaries. So, keys are assumed to come from a total order, that is an order to the keys, some order. So, normally we assume ascending descending order, or we assume lexicographic order. So, new operations that we decide is first. Now, when we talk about first here, we do not mean the first element in some data structure, we mean the first entry in the dictionary ordering. So, again it is dependent upon the organization of data. Last means last entry in the dictionary ordering, that means the smallest element and the largest element as far as the dictionary ordering is concerned. Successor is it is a iterate of entries with keys greater than or equal to k in increasing order. Similarly, predecessor is an iterator of entries which is less than or equal to k in the decreasing order. So, it depends on that. So, basically it is in order traversal. So, in order traversal will give you a sorted order. So, in that sorted order, successor of key will give you the next element and predecessor will give you the previous element in the sorted order. So, in a binary search tree, what we are trying to say is, in a binary search tree, when you do in order traversal, you get a list elements in sorted order, and when we say successor, it means the next element in the sorted order or the next element in the in order traversal, and when we say predecessor, we mean the previous element in the sorted order, whatever sorting it is, I mean the previous element, and in order traversal the previous. So, now let us go to the ADT for a binary search tree. So, we are talking in terms of abstract data types, as we know. So, the ADT for a binary search tree is similar to the ADT for general linear list with the same operations, but searching a binary search tree is more efficient than searching a linear list. A general linear list uses sequential searching, but a binary search tree uses a version of binary search. That is why it is more efficient to search in a binary search tree than it is to search in a linear list, because there we do sequential search. Here the organization and the way it has been, the data has been organized, we are actually effectively doing a binary search. As you remember, in a binary search, we just take some particular node and search, we see whether the key we want to, I am talking about a general binary search, we want to see whether the key we are looking at is lesser than or greater than that node. If it is less than, then we search in this side, if it is more, we search in this side. Of course, it has to be in sorted order. So, that is the thing. Now, let us look at the binary search tree implementation. Now, binary search tree can be implemented using either arrays or linked lists like any data structure, but linked list seems to be more suited and more efficient as far as binary search trees is concerned. And as in similar to the linked list or pointer implementation of a binary tree, the implementation uses nodes with 2 pointers left and right, as we did in binary tree. And this is an example of a binary tree where we have the left and right pointers to the node. So, as you can see, you have a node, you can have a head node pointing to the root, and the root left pointer, left points to the left subtree and right points to the right subtree. This is similar to a binary search tree, except that in a binary search tree, the organization of the data is specific. So, whenever we go to the left side, it will be less than, all the nodes will be keys will be less than, and to the right it will be greater than. So, let us look at the BST representation. As we saw, it can be represented by linked data structures of nodes, where the root T points to the root of the tree, okay, and each node contains some fields. One is the key, then left pointed to the left child root of left subtree, left child or root of the left subtree, right points to the right child or the root of the right subtree, and P is a pointer to the parent of the tree. In the case of the root, the parent is null. This is an optional representation. In some representation they use parent, some representation they do not use parent. I will tell you later why sometimes parent is used. This is basically for insertion deletion operations, especially deletion operations. We will see to that later, but mostly it will be key left and right. Sometimes there is also a parent to the node. Okay. So, when we look at the operations of a binary search tree ADT, the operations can be retrieve the item with a given search key from a binary search tree. This is a very important operation, especially when we talk about dictionaries. And traverse items in a binary tree in pre-order, in order or post order, just like we did in a binary tree. In binary search tree, the in order is important because that order determines the successor and predecessor operations. So, when you define successor and predecessor, we are talking only about successor and predecessor in the in order traversal, but like a tree you can do the any type of traversal, pre-order, in order, post order. Insert a new item into a binary search tree. So, insertion here is not insertion in front, insertion in back and things like that. This insertion is specific. You have to retain the property of the binary search tree, that is important in this particular insertion. So, even if you remove a key or insert a key, when you insert a key, the key has to follow the binary search tree property. Similarly, when you talk about deletion, the deletion of the item with a given search key you can do, but still you have to maintain the binary search tree property. So, that is the idea of insertion and deletion. So, there are certain other operations also to implement operations like the following: search for an element, add an element, get the height of the tree, get the minimum value, get the maximum value, remove the minimum value, remove the maximum value, retrieve a particular element, search for an element, remove a particular element, and print in order, print pre-order, print post-order. All these are operations that you can have. As I already told you, in any data structure, the ADT is you will have the ADT. So, the ADT here is the binary search ADT. Binary search ADT says that I have a binary tree which has a particular organization of data. So, that is fixed specification. The operations depends on the applications you put the binary search tree. For example, if you are using binary search tree for dictionary, then search is very important. Okay. And maybe inserting is important, you never delete. So, you do not have to have a delete operation. Getting the minimum, getting the maximum may be important. So, it depends on what operations you want to do. So, you can remove minimum, remove maximum, you can get the minimum, get the maximum. Of course, as we already saw before in any data set, there is a difference between get and remove. Get will just access it and give it to you, remove will remove that particular element, and you can remove a particular element if you want also. So, these are some of the operations. Which operation you choose depends on the application, and the binary search tree specification along with a set of operations will have is called one binary search tree. If you have different operations, it becomes a different binary search tree, ADT. Now, let us look at searching for the in a binary search tree. So, there are three search algorithms: finding the smallest node, finding the largest node, and finding the requested node, that is a particular node. So, the searching, let us assume we want to search for a node 15. So, we are searching for 15. If it is a root node, then we are done. If we are searching for a key less than 15, then we should search in the left subtree, that is known. There is no question of searching in the right subtree, that is the property. If you are searching for a key greater than 15, you can forget about what are all the nodes in the left subtree, you can go to the right subtree and search there. So, this is why it is called binary search, dividing the tree into two, not necessarily equal halves, okay, that we will discuss later. You are dividing into two and you are eliminating the search in one part of the tree. So, now let us look at finding the minimum and maximum in a tree. So, now this is the tree. So, let us assume we want to find the minimum element in this particular binary search tree, and we follow the left children until we reach. So, always you start from the root node. So, we start with 13, okay, and then okay. So, we start with 13, we want to find the minimum node. So, we go to the left subtree. So, the left subtree has 7 as the root, you check whether the 7 is less than 13, it will be less. So, you do not have to search for that, then you go to the left subtree. You have to just check whether the root that you have reached has a left subtree. If it does not have a left subtree, that is the minimum element. If it has a left subtree, you go to the left subtree. So, 7 has a left subtree, you go to 4, 4 has a left subtree, you go to 3, 3 has a left subtree, so you go to 1, 1 does not have a left subtree, so that is the minimum element. Now, what about maximum? You start again with the root, you go to root and you have to keep on traversing till there are no right subtrees. So, 13 has a right subtree, so you go to the right, you have 23, 23 does not have a right subtree, so 23 is the maximum element. So, this is the way of finding minimum and maximum element. Now, let us look at the algorithm. So, as we already told you, the binary search tree property guarantee is that the minimum is always located at the leftmost node. So, you keep traversing from the root left, left, left till there are no left subtrees, then that will be the smallest element. Similarly, for maximum is always located at the rightmost node. So, you keep traversing the tree from the root right subtree till there are no more right subtrees for a particular node, then that particular node is the maximum. So, this is the algorithm for tree minimum and tree maximum. So, the x is the root of the tree, while left of x is equal to null, that is till it is null, you keep traversing to the left, and when you return that node x, so x is that x will be the it will come out of the loop when x has no left subtree. So, that particular x is the is your minimum. Similarly, maximum, while right x is not equal to null, you keep traversing. So, when you come out of the loop, that x will be your rightmost node, that means it does not have a right pointer. So, that is the maximum node. So, this is the simple algorithm for tree min and tree max. Now, let us go back to searching this tree. So, binary search algorithm of an array of sorted item reduces the search space by 1/2 each time you do a comparison, two parts, one part. Okay. So, now you take this particular example. So, what we are doing here is, first I search for, let us assume I want to search for a particular node. So, depending upon all the elements 14, 41, 56 all, okay, we start with a node, we assume these are this is just for understanding of searching. So, I have the nodes 34, 41, 56, 63, 72, 89 and 95. So, I start with 63, all the nodes to the left of 63, that is 34, 41, 56 will come to the left, and 72, 89, 95 will come to the right. Okay, it depends on, anyway it will come to the right. And now, in 34, 41, 56, 34 will come to the left and 56 will come to the right. In 72, 89, 95, 72 will come to the left and 95 will come to the right. So, that is what we are trying to say. So, when you are searching for an element, say 34, you will go to 63, find 34 is less and come down. So, you will not search for 72, 89 part at of the tree at all, you will search here, then you find that 34 is less than 41. So, you search only that part of the tree, that is what we are trying to say when we say searching. Now, let us see what is the order in which we actually do a searching. Okay. Let us assume we want to search for 9, okay. We want to search for a key 9. So, what are the steps that we will use? First, we will start with compare 9 with 13, and since we find that 9 is less than 13, we will go to the left subtree. So, that is what we go to the left. Then we compare 9 with 7 and we find that 9 is greater than 7. So, we go to the right subtree where we find 8. Okay. So, we compare next 9 with 8 and we find that 9 is greater than 8. So, we go to the right subtree where we find the root to be 10. So, we compare 9 with 10 and we find that 9 is less than 10. So, we go to the left subtree, and at that point we compare 9 with the key, we find that we have reached the tree. So, this is the order in which the search will come. Okay. So, the searching the binary search tree is at every node you will search with the key with the root of that particular tree. So, you will start with the root, go to the left subtree, search at the root of the left subtree and so on. So, every time you are searching the root. So, this is the order in which search will happen. Now, let us look at the algorithm for searching a binary search tree. There are two algorithms we will be discussing. One is a recursive tree search and the other is the iterative tree search. So, the input is going to be the root of the tree, the value at the root of the tree, and the key that you want to search for. So, if the root does not exist, okay, or the if the root does not exist, that is it is null, or the key itself is at the root, then you just return that x, that is that value of the root. Now, if the k, the key that you want to search for, is less than the key at the root, then you go and return, this is the recursive algorithm, tree search left of x, that is you go to the left subtree comma the key. So, that means what you are recursively calling left tree search with the left subtree, or you call, if it is greater than, you call with tree search at the right subtree. So, this is the algorithm. The recursive tree is more straightforward to understand, because what you are doing is you search in the root, if it is equal give it out, if the tree does not exist give it as null, if it is not, then you check whether it is less than or greater than. If it is less than, you call tree search with the left subtree, if it is greater than, you call tree search with the right subtree. So, that is it in the recursive version. In the iterative version, what you will have to do is, while the key is null and the key is not equal to the root key, if the key is less than x, then you make x equal to the left of x, else you make x to the right of x. You keep doing this while there is a x. So, when you come out, you will have the tree search is more efficient and more it is on most computers, because this is a you do not keep calling a recursive, I mean you do not call a thing, it is a fairly straightforward algorithm. You go to the left, you keep going to the left. So, that is the while loop. So, until there is a null or you find the key is equal to the key that you are searching for, you have to keep on doing this operation of going to the left and going to the right. We saw how it was iteratively done in the previous example. Okay. So, the running time of this is approximately of the order of h, where h is the height of the binary search tree. Okay. Now, this height we will talk about later when we are talking about balanced tree and things like that, but as of now depending upon the height of the binary search tree, the running time of the algorithm. So, now let us go to, as I already told you, the in order traversal is very important as far as binary search tree is concerned, because we are talking about successor and predecessor in terms, but please remember pre-order and post-order is not that you cannot do pre-order post-order, just to say that in order is more important. So, a very interesting property of binary search tree is that when we apply the in order traversal, the elements that are visited are sorted in ascending order. So, there is no question of descending order and all here, because of the binary search tree property. Remember the binary search tree property, we said that the left is less than right, the root, and right is less than the root, right is greater than the root. So, when we do in order traversal, we will get it only in ascending order, because in order traversal first goes left, root and right. Now, suppose you want to get it in descending order, how we will do, we will see that later. Okay. So, let us look at the algorithm in order tree walk x. So, the x is the root node. If x is not equal to null, if it is null you cannot do anything. If it is not equal to null, then you have to, this is the recursive algorithm, you have to in order tree walk the left of p and print the left, print the key, and then in order traversal of the right of. So, every time right of x, that is every time you do the in order traversal, you finish the left side, do the root, that is the, we have already seen previously in binary search tree traversals, where we know that you, what is the binary, any in order, you have to go to the left, root, right. So, the same thing we are doing here, no difference, the in order traversal concept is not different, but what is inside those keys are in a particular order, that is all. So, now let us look at the binary search tree property allows the keys of a binary search tree to be printed in monotonically increasing order, and you can do that recursively, print it in a recursive manner, okay, in order recursively. Now, we come to two very important and interesting properties which we define for a binary search tree, the successor and predecessor of a node. So, the successor of a node x is the y such that the key of y is the smallest key that is greater than key of x. It is not anything very different, it is the sorted order. When you talk about successor of a node x, suppose I say y is the successor of the node x, then the key of y that we talk about is the smallest key that is greater than the key of x. So, x here, x and y we here we are not talking about as a key, we are talking about as the node. So, if you take a node x and I say y is the successor of node x, then it means that the key of y is the smallest key that is greater than x, okay, is the smallest key that is greater than x, okay, and the successor of the largest key is always nil, there cannot be any successor. Search consists of two cases. Now, in the successor case, if the node x has a non-empty right subtree, so if it has a non-empty right subtree, then x's successor is the minimum of the right subtree of x. So, suppose I have x, it can have two cases, it can have a non-empty right subtree or it can have an empty right subtree. If it has a non-empty subtree, then you have to go to that left right subtree of x and find the minimum node there, okay, that is what we are trying to say. Now, on the other hand, if the x has an empty right subtree, then you have to move to the left of the tree, move through the right children, we are visiting smaller keys. So, if x is successor of y is the node, that is the predecessor of x is the maximum of left subtree. In other words, x's successor y is the lowest ancestor of x whose left child is also an ancestor of x. So, if the node has an empty right subtree, then what we have to do is we have to move to the left of the tree of that particular right subtree, you have to move to the left, move through the right children, we are visiting smaller keys. So, left up the tree we are visiting the smaller keys. If x is successor of y is the node and x is the predecessor of that particular node, then in other words what we have to do is x is successor y is the lowest ancestor of y who is also an ancestor of x. We will see more interesting when we can understand it much better when we look at the example. Let us look at that. So, we are looking at successor of a node. So, this is the tree that we have with us. So, now if I go, this is the successor of the largest key is null. So, if the largest key is 213 in this particular tree, where it is, remember the largest or the maximum element is at the rightmost node. So, the rightmost node will not have a right subtree. So, the successor of this itself is null. So, that is the first thing that we are looking at. And now let us look at key 56. If you look at the key 56, it has a non-empty right subtree. Okay, that is the idea. It has a non-empty right subtree. So, if you talk about a non-empty right subtree, the successor of 56 is 100, because this is the minimum in the right subtree. So, now let us look at 56. I want to find the successor of 56. The successor of 56 is a the right subtree can be empty or non-empty. If it is non-empty, then what we have to do, you have to go to the that right subtree and find the minimum element there. So, that is the successor. Now, let us look at that is the case A. Now, let us look at this side of another tree that we are taking, and you find here that I want to find key 10, which has a empty right subtree. Now, I want to find the successor of this. Now, how do I go about this? I look at the ancestor. Now, 7 is the lowest ancestor of 10, okay, but the left child of 7 is not an ancestor of 10. That is the condition we have. I will repeat again. I have to find the lowest ancestor of 10. In this case, ancestor means you have to go up the tree and you find 7. Now, 7 is the lowest ancestor of 10, but 7 is not a ancestor of 10. Okay. So, I am sorry. But left child of 7, which is 6 is 4 is not an ancestor of 10. That is the condition. So, what we have to do? We have to go one more. So, the successor of 10 is 13, as it is the lowest ancestor of 10, where 13's left child 7 is also an ancestor of 10. So, we could not take 7, because 7's the ancestor of the left child of 7 was not an ancestor of 10, but we take 13 because 13's left child is an ancestor of 10. So, here we find that the successor of 10 is 13. Okay. So, this is the case B. This is the little interesting case, different case from case A. Case A is sort of direct. You find the minimum element. Case B, it is not like that. You have to go up the tree, find the ancestor. The ancestor you find left child also has to be an ancestor of 10. Okay. So, that is the successor of node, and this is the tree successor algorithm. If right of x is not equal to null, then you return the tree minimum right left. If it is null, then you go to the parent of x, go to the parent, and until there is no more it does not have y is not null and x is equal to right of y, then you go and find out x is equal to y, y is equal to parent of y, you return that value of y. So, that is how we do the tree successor. So, this predecessor is symmetric, similarly we can do, and the running time is again of the order of h. So, this is the predecessor of the road, similar way, except that we go for tree maximum and we go for the left instead of the right. So, we are not going to discuss that. Again the running time is of the order of h, the summary. Now, let us look at what we discussed in this module. We explained the concept of binary search trees, the binary search tree property, and what is that property. It is the binary search tree is different from the binary tree only in the organization of data, otherwise it follows the binary tree property. Discuss searching operation of binary search tree, very important if you are using a binary search tree for operations like dictionary or to represent a dictionary. And we describe the in-order traversal of binary search tree, because we are interested in successor and predecessor, and which is defined in the in-order traversal, and we explain the successor and predecessor operation associated with binary search trees. In the next module, we will be talking about the other operations of binary search trees. Thank you.